geometry of spacetime, Einstein's elegant curvature. Welcome. Tonight, we journey into one of the most profound realizations in the history of human thought, the discovery that gravity is not a force pulling objects together across empty space, but rather the very shape of space and time themselves. This is the story of how Einstein reimagined the cosmos as a four-dimensional geometric structure, curved and warped by the presence of mass and energy, where what we perceive as gravitational attraction is merely matter, following the contours of this curved spacetime along paths of least resistance. The classical world and its limits. For more than 2 centuries, Isaac Newton's law of universal gravitation served as the bedrock of our understanding of how objects attract one another. Every particle in the universe, Newton told us, attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This mathematical relationship, elegantly simple in its formulation, could predict the motion of projectiles on Earth, the orbits of moons around planets, and the paths of planets around the Sun, with remarkable precision. Newton's framework rested on certain fundamental assumptions about the nature of reality itself. Space, in his conception, was absolute, a fixed, unchanging stage upon which the drama of physical events unfolded. It existed independently of the objects within it, a three-dimensional container that extended infinitely in all directions. Time, similarly, was absolute and universal. It flowed at the same rate everywhere in the universe, ticking forward uniformly whether you stood on Earth, traveled through the void between stars, or hovered near a massive planet. A second measured here was precisely equal to a second measured anywhere else. This vision of absolute space and absolute time formed the foundation upon which classical mechanics was built. Yet even as Newton's mechanics triumphed in explaining the motions of celestial bodies, a conceptual difficulty lurked within the theory itself. The gravitational force in Newton's law acted instantaneously across any distance. If the sun were to suddenly vanish, Earth would immediately, at that very instant, cease to feel its gravitational pull and would fly off in a straight line. No time would elapse between the sun's disappearance and Earth's response. Information about the sun's absence would propagate across 150 million kilometers of space in zero time. This instantaneous action at a distance troubled many physicists, including Newton himself. How could one object know about the presence or absence of another object across vast reaches of empty space? What mechanism could possibly transmit gravitational influence at infinite speed? Newton recognized this conceptual gap but offered no solution, famously stating in his Principia that he would frame no hypotheses about the underlying cause of gravity. The mathematics worked, the predictions matched observations, and for practical purposes, that sufficed. The deeper question of how gravity actually operated remained unanswered. The situation grew more complex with the development of electromagnetism in the 19th century. James Clerk Maxwell unified electricity and magnetism into a single theoretical framework, showing that electromagnetic disturbances propagate through space as waves traveling at a finite speed, the speed of light, approximately 300,000 kilometers per second. If electromagnetic influences traveled at a finite speed, constrained by this cosmic speed limit, why should gravity be any different? The inconsistency between the instantaneous propagation of gravitational effects and the finite propagation of electromagnetic effects suggested that something fundamental in our understanding needed revision. The first revolution came in 1905 with Albert Einstein's special theory of relativity. Einstein demonstrated that space and time were not separate, absolute entities, but were intimately connected as a four-dimensional continuum called spacetime. Different observers moving relative to one another would measure different intervals of space and time, but they would agree on a particular combination of spatial and temporal measurements, the spacetime interval. Time could dilate, lengths could contract, and simultaneity became relative, depending on one's state of motion. The only absolute was the speed of light in vacuum, which all observers would measure to have the same value regardless of their motion. Special relativity resolved many puzzles but could not address gravity. The theory worked perfectly in the absence of gravitational fields, describing physics in inertial reference frames, those moving at constant velocity with no acceleration. But gravity, as Newton had shown, produces acceleration. Objects fall, orbits curve, and trajectories bend under gravitational influence. Special relativity, confined to inertial frames, could not accommodate these accelerated motions. Einstein recognized that a more general theory was needed, one that could incorporate gravity into the relativistic framework. The path to that theory would require a complete reconceptualization of what gravity actually is. The conceptual revolution. The breakthrough came to Einstein in what he later described as the happiest thought of his life. It was 1907, and Einstein was working at the patent office in Bern, Switzerland. As he sat in his chair, he imagined a person falling from the roof of a house. For that falling person, Einstein realized, the gravitational field would not exist. The person would feel weightless during the fall, just as astronauts feel weightless while orbiting Earth. Any object the person released would remain suspended relative to them, neither falling nor rising, as both the person and the object accelerated downward together at the same rate. This seemingly simple observation contained the seed of a profound idea. The experience of someone in free fall is indistinguishable from the experience of someone floating in empty space, far from any gravitating bodies. Both are weightless. Both see objects around them remaining at rest relative to themselves. Conversely, a person standing still on Earth's surface feels their weight. They feel the ground pushing up on their feet. This experience is indistinguishable from the experience of someone in a rocket accelerating through empty space at 9.8 meters per second squared. The acceleration due to Earth's gravity. The floor of the rocket would push up on their feet with exactly the same force. From these thought experiments, Einstein formulated what he called the equivalence principle. In its simplest form, the principle states that the effects of gravity are locally indistinguishable from the effects of acceleration. No experiment performed in a small enough region of space and over a short enough period of time can tell you whether you're in a gravitational field or in an accelerating reference frame. The two situations are equivalent. This equivalence had radical implications. If free fall in a gravitational field is equivalent to inertial motion, motion at constant velocity with no forces acting, then perhaps objects in free fall aren't being pulled by a force at all. Perhaps they're simply following their natural paths through space-time, just as an object in empty space follows a straight line at constant velocity. The apparent acceleration we observe when an apple falls from a tree would not be due to a force pulling the apple downward, but rather due to the fact that the ground is accelerating upward relative to the apple's natural path. The apple is trying to follow its natural trajectory through space-time, but the surface of Earth gets in the way, pushing it off that trajectory and creating the sensation of weight. But how could this be? How could an object falling toward Earth actually be following a path equivalent to straight-line motion? The answer Einstein came to realize is that space-time itself is curved near massive objects. The paths that objects follow in free fall, what we call orbits or falling trajectories, are actually the straightest possible paths through curved space-time. In the language of geometry, these paths are called geodesics. To understand geodesics, imagine drawing the shortest route between two cities on Earth's curved surface. Because Earth is spherical rather than flat, the shortest path is not a straight line as it would be on a flat map, but rather an arc of a great circle, the type of curve you get by intersecting Earth with a plane that passes through its center. Airlines follow these great circle routes because they minimize the distance traveled. Yet from the perspective of someone walking along such a path on Earth's surface, it feels straight. You don't need to turn left or right. You simply walk forward, and the curvature of Earth's surface naturally guides your path. Geodesics in space-time work similarly. They are the paths through four-dimensional space-time that represent the longest proper time, the time as measured by a clock traveling along that path, between two events. For objects moving much slower than light, maximizing proper time is equivalent to minimizing the spatial path, analogous to great circles on Earth. An object in freefall, unimpeded by external forces, follows a geodesic. It takes the straightest path through space-time, even though space-time itself may be curved. Earth's surface, by preventing an apple from following its geodesic path through space-time, must exert a force on the apple. This is the normal force we feel as our weight. From the perspective of general relativity, the ground beneath our feet is constantly accelerating upward, pushing us off the geodesic path we would naturally follow in free fall. The curvature of space-time explains why all objects in Earth's gravitational field, regardless of their mass or composition, fall with the same acceleration. They're all simply following geodesics through the same curved space-time geometry. This geometric interpretation resolved the problem of action at a distance. Gravity doesn't need to propagate instantaneously from one object to another because gravity isn't a force transmitted between objects. Instead, mass and energy curve the space-time around them, and this curvature influences the motion of other objects by determining the geodesic paths they follow. Changes in the distribution of mass and energy cause changes in space-time curvature, and these changes propagate as ripples through space-time, gravitational waves, traveling at the speed of light, not instantaneously. The transition from thinking of gravity as a force to thinking of it as space-time curvature represents one of the most dramatic paradigm shifts in physics. It required abandoning centuries of intuition about how the universe works. But it also promised something profound, a complete unification of geometry and physics where the shape of space-time is determined by the distribution of matter and energy, and that shape in turn determines how matter and energy move. The physicist John Wheeler captured this reciprocal relationship in a memorable phrase. Matter tells space-time how to curve, and curved space-time tells matter how to move. To make this vision mathematically precise, Einstein needed the tools of differential geometry, the mathematics of curved spaces. These tools had been developed decades earlier by mathematicians studying abstract geometric structures with no thought that they might describe physical reality. Einstein's genius lay in recognizing that these mathematical concepts were exactly what he needed to formulate his new theory of gravity. The mathematical foundation, Riemannian geometry. The mathematical framework underlying Einstein's geometric theory of gravity is Riemannian geometry, named after the 19th century German mathematician Bernhard Riemann. Riemann had asked a fundamental question: what does it mean for a space to be curved, and how can we describe that curvature mathematically without referencing any higher dimensional space into which the curved space might be embedded? His work laid the groundwork for understanding intrinsic curvature, curvature that can be detected by measurements made entirely within the space itself, without needing to step outside it. At the heart of Riemannian geometry lies the concept of a manifold. A manifold is, roughly speaking, a space that locally resembles flat Euclidean space but may have a different global structure. The surface of Earth provides an intuitive example. If you examine a small enough patch of Earth's surface, say the floor of a room, it appears flat. You can use ordinary Euclidean geometry to measure distances and angles, and everything works as expected. But if you zoom out and consider larger distances, Earth's curvature becomes apparent. The rules of Euclidean geometry no longer hold exactly. The sum of angles in a large triangle drawn on Earth's surface exceeds 180 degrees. Parallel lines, if extended far enough, eventually converge. Spacetime in general relativity is a four-dimensional manifold, 3 dimensions of space and 1 of time. Each point in spacetime represents an event, something that happens at a particular location, at a particular moment. To do physics on this manifold, we need to be able to measure distances and times to calculate how far apart events are in spacetime. This is where the metric tensor comes in. The metric tensor is a mathematical object that tells us how to compute the spacetime interval between nearby events. In special relativity on flat spacetime, the metric takes a simple form, known as the Minkowski metric. It defines the interval between two nearby events as a combination of their separation in time and their separation in space. Specifically, the squared interval equals the square of the time separation minus the sum of the squares of the spatial separations in each direction. This minus sign between time and space is crucial. It reflects the fundamental difference between time-like and space-like directions in spacetime. In general relativity, the metric tensor becomes more complicated because spacetime is curved. The metric components are no longer constants but become functions of position and time. They vary from point to point in spacetime, encoding information about the local geometry. Where spacetime is strongly curved, near a black hole for instance, the metric components differ significantly from their flat space values. Where spacetime is nearly flat, far from any massive objects, the metric components approach those of the Minkowski metric. To navigate through curved spacetime, we need a concept of parallel transport, a way to compare vectors at different points. In flat space, this is straightforward. A vector pointing north in New York still points north when parallel transported to Los Angeles. But on a curved surface, parallel transport becomes path-dependent. If you start at Earth's equator with a vector pointing north, transport it northward to the North Pole while keeping it parallel to itself, then transport it southward along a different line of longitude back to the equator, the vector will point in a different direction than when it started. It will have rotated. The amount of rotation depends on the area enclosed by the path and is a direct measure of the surface's curvature. The mathematical machinery for handling parallel transport involves the Christoffel symbols named after German mathematician Elwin Bruno Christoffel. These symbols, derived from the metric tensor and its derivatives, describe how basis vectors change from point to point. They encode the connection, the geometric structure that tells us how to differentiate vector fields on curved manifolds. Although Christoffel's symbols have many components and can appear complex, they're not fundamental tensors themselves. Their values depend on the choice of coordinate system, and they can be made to vanish at any single point by choosing appropriate coordinates. This reflects the equivalence principle. In a small enough region of space-time, you can always find a freely falling reference frame where the effects of gravity temporarily disappear and space-time looks flat. But while you can make the Christoffel symbols vanish at a single point, you cannot generally make them vanish throughout an extended region if spacetime is truly curved. The failure of Christoffel's symbols to vanish everywhere, the path dependence of parallel transport, and the geodesic deviation, the tendency of initially parallel geodesics to converge or diverge, all point toward the existence of intrinsic curvature. The mathematical object that captures this intrinsic curvature is the Riemann curvature tensor. The Riemann curvature tensor. The Riemann curvature tensor is the central object describing the geometry of curved spacetime. It is a mathematical entity with four indices, representing its action on four different directions in spacetime. The tensor encodes complete information about how spacetime curves at each point, information that cannot be eliminated by any choice of coordinates. To understand what the Riemann tensor measures, consider the process of parallel transporting a vector around a closed loop in spacetime. In flat spacetime, if you take a vector, move it around any closed path while keeping it parallel to itself at each step and return to your starting point, the vector will point in the same direction as when you began. The loop has no effect, but in curved spacetime, the vector will generally return pointing in a different direction. It will have rotated by some angle that depends on both the path taken and the curvature of the spacetime within the region enclosed by the path. The Riemann tensor quantifies this failure of vectors to return to their original orientation. More precisely, it measures the commutator of covariant derivatives, the extent to which the order of differentiation matters when you take second derivatives of vector fields. In flat space, mixed partial derivatives commute. The order of differentiation doesn't matter. The derivative with respect to x and then y gives the same result as the derivative with respect to y and then x. But on a curved manifold, covariant derivatives generally don't commute. The Riemann tensor captures exactly this non-commutativity, providing a coordinate-independent measure of curvature. The Riemann tensor possesses remarkable symmetry properties. It is antisymmetric in its first pair of indices, and in its second pair of indices, it remains unchanged if you swap the first pair with the second pair, and it satisfies a cyclic identity known as the first Bianchi identity, which relates components with cyclically permuted indices. These symmetries drastically reduce the number of independent components. In four-dimensional spacetime, what might seem like 256 components, four choices for each of four indices, actually reduces to only 20 independent components due to these symmetries. One particularly important aspect of the Riemann tensor is its connection to geodesic deviation. Imagine two particles initially at rest relative to each other, both in free fall. In flat spacetime, they would remain at constant separation forever, moving on parallel geodesics. But in curved spacetime, the separation between them will change. They will accelerate toward or away from each other, even though no force acts between them. This is tidal gravity, the differential gravitational effect across an extended object. The Riemann tensor determines the rate of this geodesic deviation. It appears directly in the geodesic deviation equation, which describes how the separation vector between nearby geodesics evolves. From the Riemann tensor, we can construct simpler objects by a process called contraction, summing over pairs of indices. The most important contraction gives the Ricci tensor, which has two indices and represents a kind of average curvature. The Ricci tensor captures information about how volumes change in curved space. In a region of positive Ricci curvature, the volume of a small ball is less than it would be in flat space. Geodesics initially pointing outward from a point tend to converge. In a region of negative Ricci curvature, volumes expand more than in flat space and geodesics diverge. We can contract once more, summing over the two indices of the Ricci tensor to obtain the Ricci scalar, a single number at each point representing the total curvature in all directions. The Ricci scalar plays a crucial role in Einstein's field equations, serving as the scalar curvature that appears in the action principle from which those equations can be derived. But neither the Ricci tensor nor the Ricci scalar contains all the information in the Riemann tensor. Some curvature information remains in what's called the Weyl tensor, which represents the part of the Riemann tensor not determined by the Ricci tensor. The Weyl tensor describes tidal distortions, shape changes without volume changes. In vacuum regions, where no matter is present, the Ricci tensor vanishes, but the Weyl tensor generally does not. It describes how spacetime can be curved even in empty space, carrying information about gravitational fields produced by distant matter. The mathematical richness of the Riemann curvature tensor reflects the physical richness of gravity in general relativity. Unlike Newtonian gravity, where a single function, the gravitational potential, describes the field at each point, general relativity requires 20 independent functions to fully specify spacetime curvature. This additional complexity allows general relativity to describe phenomena Newtonian gravity cannot. Gravitational waves, black hole horizons, the expansion of the universe, and the extreme warping of spacetime near ultra-dense objects. Einstein's field equations. Einstein sought equations that would relate spacetime geometry, embodied in the metric tensor and its curvature, to the distribution of matter and energy. The form these equations should take was guided by several principles. First, they should reduce to Newton's law of gravity in the limit of weak gravitational fields and slow motion, ensuring consistency with centuries of successful predictions. Second, they should be consistent with special relativity in the absence of gravity. Third, they should respect the principle of general covariance, meaning the equations should take the same form in any coordinate system. Finally, they should ensure conservation of energy and momentum. The key to satisfying these requirements lay in constructing the right combination of curvature tensors. The Ricci tensor alone wouldn't work. It has the wrong behavior under certain transformations and doesn't automatically enforce conservation. Einstein's insight was to form what's now called the Einstein tensor, a particular combination of the Ricci tensor and the Ricci scalar multiplied by the metric tensor. The Einstein tensor has the crucial property that its divergence vanishes identically, a consequence of the Bianchi identities satisfied by the Riemann tensor. This means that if you set the Einstein tensor equal to something representing matter and energy, the conservation of that matter and energy automatically follows from the geometry. This is exactly what Einstein wanted, a theory where conservation laws emerge naturally from the geometric structure rather than being imposed as separate assumptions. On the other side of the equation sits the stress-energy tensor, a mathematical object describing the density and flux of energy and momentum. The stress-energy tensor has 16 components in four-dimensional space-time, but symmetry reduces this to 10 independent components, exactly matching the 10 independent components of the Einstein tensor. The time-time component of the stress-energy tensor represents energy density. The time-space components represent momentum density, or equivalently, energy flux. The space-space components represent momentum flux, pressures and stresses within matter. The Einstein field equations state that the Einstein tensor at each point equals 8pi times Newton's gravitational constant divided by the speed of light to the fourth power, all multiplied by the stress-energy tensor. This proportionality constant ensures that the equations reduce to Newton's law in the appropriate limit. The factor of 8pi arises from matching the Newtonian prediction for weak, static, gravitational fields. These equations are deceptively compact. Written in coordinate form, they expand into 10 coupled nonlinear partial differential equations for the 10 independent components of the metric tensor. The non-linearity means that solutions don't simply add. The gravitational field of two objects isn't just the sum of their individual fields. Gravity in general relativity can interact with itself, a consequence of the fact that gravitational energy itself acts as a source of space-time curvature. Sometimes, a cosmological constant term is added to Einstein's equations. This term, denoted lambda, represents a constant energy density of empty space itself, what we now call dark energy or vacuum energy. Einstein originally introduced the cosmological constant to allow static universe solutions, balancing gravitational attraction with a repulsive effect. He later called this his greatest blunder, after Hubble's discovery that the universe is expanding showed that static solutions were physically unnecessary. Ironically, modern observations suggest the universe's expansion is accelerating, which can be explained by a positive cosmological constant. The cosmological constant has made a comeback as a central component of the standard cosmological model. The meaning of Einstein's equations can be summarized in Wheeler's memorable phrase mentioned earlier. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. More precisely, the stress-energy distribution on the right side of the equations determines the Einstein tensor on the left, which in turn determines the Ricci curvature and constrains the full Riemann curvature. This curvature then enters the geodesic equation and the geodesic deviation equation, determining how freely falling particles move and how tidal forces stretch and compress extended objects. The equations embody a profound unity between geometry and physics. In classical mechanics, the gravitational field is something added to space and time, an extra structure overlaid on the stage where physics happens. In general relativity, the gravitational field becomes part of the stage itself. Space-time geometry is the gravitational field. There is no gravitational force in the usual sense, only the curvature of space-time and the tendency of objects to follow geodesics in that curved geometry. Solving Einstein's field equations exactly is extraordinarily difficult. The 10 coupled nonlinear partial differential equations generally require approximation methods or restrictive symmetry assumptions. Only a handful of exact solutions are known, each corresponding to highly symmetric situations: empty, flat spacetime, the spacetime around a spherically symmetric non-rotating mass, the spacetime around a rotating mass, uniformly expanding cosmological spacetimes, and a few others. Yet these special solutions describe physically important situations: black holes, gravitational waves, the expanding universe, and they provide the foundation for understanding more complex scenarios through perturbative approximations. Geodesics, the straightest possible paths. Central to understanding how objects move in curved spacetime is the concept of the geodesic, the path that extremizes proper time, the time measured by a clock moving along that path. In flat spacetime, geodesics are straight lines. In curved spacetime, they bend and curve in ways determined by the local geometry. The geodesic equation can be derived from a variational principle similar to how the path of a projectile in classical mechanics can be found by minimizing action. For a massive particle moving through space-time, the geodesic is the path that maximizes the proper time between two events, the path for which a clock carried by the particle shows the longest elapsed time. This might seem counterintuitive. Why maximum rather than minimum? The answer lies in the signature of the space-time metric, the minus sign between time and space. This sign flip means that for time-like paths, paths that can be followed by massive particles moving slower than light, longer proper time corresponds to straighter paths. The geodesic equation itself is a second-order differential equation relating the acceleration of a particle to the Christoffel symbols and the particle's velocity. It states that the acceleration in any direction equals a sum of terms, each proportional to the product of two velocity components and a Christoffel symbol. When Christoffel symbols vanish, as they do in flat spacetime with Cartesian coordinates, the geodesic equation reduces to the statement that acceleration is zero. Particles move in straight lines at constant velocity, exactly as Newton's first law requires. In curved spacetime, Christoffel symbols generally don't vanish, and geodesics curve. A particle in free fall around Earth, for example, follows an elliptical geodesic through spacetime. From the particle's perspective, it experiences no force. It is weightless, in free fall. From the perspective of someone on Earth's surface, the particle appears to orbit, accelerating toward Earth's center. Both descriptions are correct, viewed from different reference frames. The particle follows the straightest possible path through curved space-time, but that path appears curved when projected onto three-dimensional space. Geodesics come in three types, distinguished by the sign of their tangent vector's squared length. Time-like geodesics have tangent vectors with positive squared length when using the conventional metric signature. These are the paths followed by massive particles moving slower than light. Every massive object traces out a time-like world line through spacetime, and if that object is in free fall, its world line is a time-like geodesic. A clock moving along a time-like geodesic measures proper time, and the geodesic maximizes this proper time among all nearby paths connecting the same events. Null geodesics have tangent vectors with zero squared length. These are the paths followed by light rays and other massless particles that travel at exactly the speed of light. Light, having no mass, doesn't have a proper time in the usual sense. A photon doesn't experience the passage of time, but light still follows geodesics, null geodesics, determined by space-time curvature. When we observe that light bends near massive objects, what we're seeing is light following null geodesics through curved space-time. Space-like geodesics have tangent vectors with negative squared length. No physical particle can follow a space-like geodesic because doing so would require traveling faster than light. Space-like geodesics represent the shortest spatial distances between events that occur simultaneously in some reference frame. They play a role in defining spatial geometry on surfaces of constant time, but they don't correspond to possible particle trajectories. The geodesic equation reveals a remarkable universality. All particles, regardless of their mass, composition, or internal structure, follow the same geodesics if they have the same position and velocity. A feather and a hammer, dropped simultaneously on the moon, fall together, arriving at the surface at the same instant. This universality puzzled Galileo and Newton, who had to assume that gravitational mass and inertial mass, conceptually distinct quantities, happened to be exactly proportional. In general relativity, the mystery dissolves. There is only one kind of mass, and all objects follow geodesics determined solely by space-time geometry, not by their individual properties. The geodesic deviation equation extends these ideas to describe how initially parallel geodesics, representing nearby particles in freefall, converge or diverge due to space-time curvature. This equation directly involves the Riemann curvature tensor, providing another way to understand what curvature means physically. Tidal forces, which stretch objects in one direction while compressing them in another, arise from geodesic deviation. The Riemann tensor, through the geodesic deviation equation, determines the strength and pattern of these tidal effects. Consider the moon's gravitational effect on Earth's oceans. The side of Earth nearest the moon feels slightly stronger gravity than Earth's center, which in turn feels stronger gravity than the side farthest from the moon. This differential acceleration, tidal force, stretches Earth along the Earth-Moon line. The geodesics, followed by water on the near side at Earth's center and on the far side, are all different, converging and diverging in a pattern determined by the Riemann tensor components of the moon's gravitational field. The result is the familiar twice-daily rise and fall of ocean tides. Near black holes, tidal forces become extreme. An object falling toward a stellar mass black hole would be stretched radially and compressed laterally with forces strong enough to tear apart any material structure long before reaching the event horizon. This process, informally called spaghettification, is a dramatic manifestation of geodesic deviation in strongly curved spacetime. The Riemann tensor components near a black hole become so large that the geodesic deviation equation predicts destructive tidal accelerations. Understanding geodesics and geodesic deviation provides the bridge between the abstract mathematics of curved space-time and the concrete predictions of general relativity. Every trajectory of a freely falling object, every orbit of a planet or satellite, every path of a light ray, all are geodesics in space-time, solutions to the geodesic equation in the curved geometry determined by mass and energy through Einstein's field equations. The Schwarzschild solution. The first exact solution to Einstein's field equations, found by Carl Schwarzschild in 1916, just months after Einstein published his theory, describes the space-time geometry around a spherically symmetric, non-rotating, uncharged mass. Despite its simplicity assumptions, the Schwarzschild solution has profound physical significance. It describes the spacetime outside any spherically symmetric object, a planet, a star, or a black hole, and it exhibits features that dramatically illustrate the differences between Newtonian gravity and general relativity. The Schwarzschild metric depends on only two quantities: the mass of the central object and the radial distance from its center. Far from the mass, spacetime approaches flatness, and the metric components approach those of flat Minkowski spacetime. Close to the mass, spacetime curvature grows stronger, and the metric components deviate increasingly from their flat space values. A special radius appears in the Schwarzschild solution, now called the Schwarzschild radius, equal to twice Newton's gravitational constant times the mass divided by the speed of light squared. For the Sun, this radius is approximately 3 kilometers. For Earth, it's about 9 millimeters. At the Schwarzschild radius, something remarkable happens. The metric components that determine the geometry undergo dramatic changes. The coefficient of the radial coordinate differential becomes infinite, while the coefficient of the time coordinate differential becomes zero. When Schwarzschild first published his solution, these apparent infinities at the Schwarzschild radius caused confusion. Many physicists, including Einstein initially, believed they represented a physical singularity where spacetime itself became pathological. It took decades to understand that the infinities at the Schwarzschild radius are merely coordinate singularities, artifacts of the particular coordinate system used, rather than genuine physical singularities. By choosing different coordinates, such as Kruskal-Szekeres coordinates or Eddington-Finkelstein coordinates, the metric remains perfectly well-behaved at the Schwarzschild radius. What the Schwarzschild radius actually represents is an event horizon, a boundary in spacetime with a remarkable one-way property. Events occurring inside the Schwarzschild radius cannot influence events outside. Light emitted from within cannot escape to the exterior. Any object or signal that crosses inward through the event horizon can never return. The event horizon divides spacetime into two causally disconnected regions: the exterior, which can send signals in both directions, and the interior, which can only receive signals from outside but cannot send signals out. For ordinary stars and planets, the Schwarzschild radius lies deep within their material interior, buried beneath layers of matter where the Schwarzschild solution doesn't apply. The actual spacetime inside a star is described not by the vacuum Schwarzschild solution, but by interior solutions that match smoothly to the exterior Schwarzschild geometry at the star's surface. The event horizon exists only as a mathematical curiosity, never manifesting physically. But if enough mass concentrates within its own Schwarzschild radius, the event horizon becomes real and accessible. This is a black hole, a region of spacetime where gravity has become so strong that not even light can escape. The boundary of this region is the event horizon, located precisely at the Schwarzschild radius for a non-rotating black hole. At the center of the Schwarzschild geometry lies a genuine physical singularity, a point where space-time curvature becomes infinite and the classical theory breaks down. All matter that crosses the event horizon inevitably falls toward this central singularity, reaching it in a finite amount of proper time as measured by a falling clock. The singularity represents a boundary of space-time itself, not a place within space-time, but a place where space-time ends. The Schwarzschild solution predicted observable effects that differ from Newtonian gravity. One of the most famous is the precession of Mercury's orbit. In Newtonian gravity, Mercury should trace out a perfect ellipse around the Sun, repeating the same path indefinitely. In reality, Mercury's orbit slowly rotates in space. The point of closest approach to the Sun, the perihelion, advances by about 5,600 arcs, seconds per century, a tiny but measurable effect. Most of this precession can be explained by the gravitational perturbations of other planets, particularly Jupiter and Venus, pulling on Mercury and causing its orbit to rotate. But after accounting for all known Newtonian effects, a residual of 43 arcseconds per century remained unexplained. This small discrepancy had puzzled astronomers for decades. Various explanations were proposed, including an undiscovered planet closer to the Sun than Mercury, but none proved convincing. Einstein's general relativity, using the Schwarzschild solution to calculate Mercury's geodesic orbit around the Sun, predicted exactly this residual precession. The calculation emerges naturally from solving the geodesic equation in Schwarzschild spacetime, accounting for the way spacetime curvature affects Mercury's path. The agreement between theory and observation, 43 arcseconds per century, matching perfectly, provided one of the first major confirmations of general relativity. Einstein later recalled that when he obtained this result, he experienced heart palpitations and felt something within him snap into place. The theory worked. The Schwarzschild solution also predicts gravitational time dilation, the slowing of clocks in stronger gravitational fields. A clock at a lower height, closer to a massive object, ticks more slowly than a clock at a higher height, farther from the mass. The effect is quantified by the metric component that multiplies the time coordinate differential. This component, called the lapse function, decreases as you approach the mass, meaning that proper time, the time measured by a local clock, elapses more slowly deeper in the gravitational field. For weak fields like Earth's, the time dilation is small but measurable with precise atomic clocks. A clock at sea level runs slower than a clock on a mountaintop by about 1 part in 10 to the 16th per meter of altitude difference. The global positioning system must account for this effect. GPS satellites orbit at high altitudes where gravitational time dilation causes their clocks to run faster than ground-based clocks by about 45 microseconds per day. Combined with special relativistic time dilation from their orbital velocity, which makes them run slower, the net effect is that satellite clocks gain about 38 microseconds per day relative to ground clocks. Without corrections for general relativity, GPS positions would drift by kilometers within a single day. Near a black hole's event horizon, gravitational time dilation becomes extreme. As viewed by a distant observer, a clock falling toward a black hole appears to tick ever more slowly as it approaches the horizon, asymptotically freezing as it reaches the horizon. The infalling clock never appears to cross the horizon from the perspective of someone watching from far away. Light signals from the clock become increasingly redshifted, stretched to longer and longer wavelengths until they fade beyond detectability. Yet from the perspective of the falling clock itself, nothing special happens at the horizon. It crosses smoothly in a finite proper time, noticing only the increasingly strong tidal forces as it continues toward the central singularity. This difference between the perspective of distant observers and the perspective of infalling observers illustrates a key feature of general relativity. Coordinate-dependent quantities, like the time it takes to reach the horizon, can vary dramatically depending on the reference frame, but coordinate-independent quantities, like proper time along a world line, are absolute and observer-independent. Gravitational lensing. One of the most spectacular predictions of general relativity is that light, despite having no mass, is deflected by gravity. This occurs because light follows null geodesics through curved spacetime, and the curvature caused by massive objects bends these geodesics, causing light rays to curve. Einstein calculated the deflection of starlight passing near the sun's limb. A ray of light grazing the sun's surface should bend by approximately 1.75 arcseconds, roughly 8 millionths of a degree. This bending angle is twice what Newtonian gravity would predict if you treated light as having a tiny mass. The factor of 2 comes from the fact that in general relativity, both the spatial curvature and the time dilation contribute to the light's deflection, whereas a Newtonian calculation would include only the spatial effect. The opportunity to test this prediction came during a total solar eclipse, when stars near the sun become visible. In 1919, British astronomer Arthur Eddington led expeditions to Sobral, Brazil, and Principe, an island off the coast of West Africa, to photograph star fields around the sun during the solar eclipse of May 29th. By comparing the apparent positions of stars near the sun during the eclipse with their positions when the sun was elsewhere in the sky, Eddington's team could measure the deflection. The results, announced later that year, confirmed Einstein's prediction within the measurement uncertainties. The deflection matched the 1.75 arcseconds predicted by general relativity rather than the 0.875 arcseconds predicted by Newtonian theory. The announcement made headlines worldwide and transformed Einstein from a respected physicist into an international celebrity. "Lights all askew in the heavens," proclaimed the New York Times. Einstein theory triumphs. This gravitational deflection of light is now called gravitational lensing, in analogy to the way glass lenses bend light. Massive objects act as gravitational lenses, bending the paths of light rays from more distant sources. The effect has become a powerful tool in modern astronomy. When a massive galaxy or cluster of galaxies lies between Earth and a more distant object, such as a quasar, the intervening mass acts as a gravitational lens. Multiple images of the background source can appear, arranged in patterns determined by the lens geometry. If the alignment is nearly perfect, the background source appears smeared into a ring, an Einstein ring, surrounding the lensing mass. These rings provide direct visual evidence of space-time curvature. Gravitational lensing is classified into strong lensing and weak lensing depending on the degree of distortion. Strong lensing produces multiple distinct images, or dramatic arcs and rings. It occurs when the alignment is favorable and the lensing mass is large. Galaxy clusters, containing thousands of galaxies and vast amounts of dark matter, are powerful, strong lenses. Images from the Hubble Space Telescope and other observatories show numerous examples of distant galaxies lensed into arcs and multiple images by foreground clusters. Strong lensing allows astronomers to measure the masses of galaxy clusters, including the dark matter that dominates their mass but doesn't emit light. The amount of lensing distortion depends directly on the total mass along the line of sight. By modeling how light is bent, astronomers can reconstruct the mass distribution of the lensing cluster. These measurements have provided some of the strongest evidence for dark matter's existence. Weak lensing produces smaller distortions that don't create multiple images, but subtly alter the shapes of background galaxies. Statistical analysis of these subtle shape changes across large areas of sky reveals the distribution of matter, both visible and dark, in the universe. Cosmic shear, the pattern of weak lensing induced by the large-scale structure of the universe, has become a key observable in cosmology, helping to constrain models of structure formation and the nature of dark energy. Microlensing occurs when a relatively small mass, such as a star or planet, passes in front of a more distant star. The lensing doesn't produce resolvable multiple images, but it temporarily brightens the background star as the foreground object's gravitational field focuses light toward Earth. Microlensing surveys monitor millions of stars, watching for these rare brightening events. When a planet orbits the lensing star, it can produce a distinctive signature in the brightening curve, allowing detection of planets around distant stars that are otherwise too faint and far away to observe directly. Gravitational lensing has even been used to detect individual planets in other galaxies, objects millions of light years away that are far beyond the reach of conventional detection methods. The statistical properties of microlensing events provide information about the prevalence of planets, the distribution of stellar masses, and the amount of compact dark matter in the Milky Way's halo. In recent years, gravitational lensing of gravitational waves has been considered. If a gravitational wave from a distant merger passes through a massive intervening galaxy or cluster, the wave can be lensed, potentially producing multiple arrivals of the same wave at Earth from slightly different directions and at slightly different times. No confirmed detection of lensed gravitational waves has occurred yet, but future gravitational wave observatories with improved sensitivity may detect such events, opening yet another window onto the universe's matter distribution. The phenomenon of gravitational lensing vividly demonstrates that spacetime is truly curved. The bending of light isn't due to some force acting on photons. Photons have no mass and don't respond to forces in the conventional sense. Rather, light follows the contours of curved spacetime, tracing null geodesics that bend around massive objects. Every gravitationally lensed image is a visible manifestation of Einstein's geometric theory of gravity, black holes, and extreme curvature. Black holes represent the most extreme manifestation of space-time curvature, regions where gravity has become so intense that space and time exchange roles, where the future points inevitably inward, and where the classical theory itself eventually breaks down. The defining feature of a black hole is its event horizon, a boundary in space-time from which nothing can escape. The event horizon is not a physical surface, but rather a null hypersurface, a three-dimensional boundary in four-dimensional space-time that light rays can cross in one direction but not the other. Once anything crosses the event horizon moving inward, its future light cone tips entirely inward. Every direction it can move points toward the singularity. Even standing still is impossible. Moving toward the singularity isn't a choice, but an inevitable consequence of the space-time geometry. Outside the event horizon, escape is still possible. An object can hover at a fixed distance from a black hole if it accelerates outward continuously, resisting the inward pull of geodesics. A spaceship with powerful rockets can maintain a stable position, though the required thrust grows larger as it hovers closer to the horizon. At the horizon itself, maintaining position would require infinite acceleration. Light emitted outward from the horizon remains at the horizon, neither falling in nor escaping out. Inside the horizon, no amount of thrust can prevent infall toward the singularity. The event horizon's radius for a non-rotating black hole is the Schwarzschild radius, directly proportional to the black hole's mass. For a black hole with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. For a black hole with 1 million solar masses, typical of those in galactic centers, the radius is about 3 million kilometers, roughly 4 times the Sun's diameter. For the supermassive black hole at our galaxy's center, with about 4 million solar masses, the event horizon has a radius of about 12 million kilometers. Tidal forces near black holes depend not just on the gravitational strength, but on the rate at which gravity changes with position, a direct consequence of space-time curvature encoded in the Riemann tensor. For a stellar mass black hole, tidal forces become extreme well before reaching the horizon. A human falling feet first towards such a black hole would experience a difference in gravitational acceleration between their feet and head of many millions of Gs when still a few Schwarzschild radii away. The person would be stretched vertically and compressed horizontally with irresistible force, a process colorfully termed spaghettification. Interestingly, tidal forces at the horizon scale inversely with the square of the black hole's mass. For a supermassive black hole, the tidal forces at the horizon are much weaker than for a stellar mass black hole. An astronaut crossing the event horizon of a billion solar mass black hole might not notice anything unusual at the moment of crossing. The tidal forces would be gentle, comparable to those experienced in Earth's gravitational field. Only later, deeper inside and closer to the singularity, would tidal forces grow destructive. The Schwarzschild solution describes non-rotating black holes, but realistic black holes form from rotating stars and should therefore rotate themselves. The spacetime around a rotating black hole is described by the Kerr solution, found by Roy Kerr in 1963. Rotating black holes are more complex than their non-rotating counterparts. They possess two horizons, an outer event horizon and an inner Cauchy horizon. Between these horizons lies a region called the ergosphere, where space-time itself is dragged around the black hole's rotation axis in a phenomenon called frame dragging. Within the ergosphere, nothing can remain stationary relative to distant stars. All objects, even light, must rotate around the black hole in the same direction as its spin. This doesn't mean everything falls in. Escape is still possible from the ergosphere, but remaining stationary is not. The dragging of spacetime by rotation is a purely general relativistic effect with no Newtonian analog. Frame dragging occurs around any rotating mass, not just black holes, but the effect is usually tiny. Earth's rotation drags spacetime around it, but the effect is so small that it was only detected in 2011 by the Gravity Probe B satellite after decades of effort and extraordinary measurement precision. Near a rapidly rotating black hole, frame dragging becomes dramatic, dominating the space-time structure in the ergosphere. The Kerr solution exhibits another remarkable feature. The singularity at its center is not a point, but a ring. The ring lies in the equatorial plane and has a radius that depends on the black hole's spin. The ring singularity is a place where space-time curvature becomes infinite, much like the point singularity in a Schwarzschild black hole. But its structure allows for some exotic possibilities suggested by the mathematics, though their physical realizability remains uncertain. The existence of black holes was long considered theoretical speculation. Although the mathematics was clear, it seemed possible that nature might avoid forming such extreme objects. Perhaps stellar collapse would always halt before reaching the event horizon, through some unknown mechanism. Perhaps naked singularities, singularities without event horizons, would form instead, which would be observationally very different. These concerns were addressed by singularity theorems proven by Roger Penrose, Stephen Hawking, and others in the 1960s and 1970s. These theorems showed that under reasonable physical conditions, positive energy density, no exotic matter, gravitational collapse to a singularity is inevitable once certain points of no return are passed. Cosmic censorship conjectures, still unproven rigorously but widely believed, suggest that singularities always hide behind event horizons, never appearing naked to external observers. Observational evidence for black holes accumulated steadily from the 1970s onward. X-ray binary systems, where a visible star orbits a compact, unseen companion, and matter flowing from the star to the companion emits X-rays, provided early candidates. By measuring orbital dynamics, astronomers could estimate the compact object's mass. Some systems showed companions exceeding 3 solar masses, above the maximum possible mass for neutron stars. These systems were strong black hole candidates, though definitive proof remained elusive. The case strengthened with observations of galactic centers. Stars near the center of our Milky Way orbit a compact dark object with measurements indicating a mass of about 4 million suns within a region smaller than our solar system. No known object, except a black hole, could be so massive and compact. Similar observations at other galactic centers revealed supermassive black holes with masses from millions to billions of solar masses. The ultimate confirmation came in 2019, when the Event Horizon Telescope collaboration released the first image of a black hole's shadow, the dark silhouette cast by the event horizon against the bright glow of infalling matter. The target was the supermassive black hole at the center of the galaxy M87, 55 million light-years away. The image showed a bright ring of emission surrounding a dark central region, exactly as predicted by general relativity. The size and shape of the shadow matched theoretical expectations for a black hole with the measured mass. In 2022, the Event Horizon Telescope imaged the black hole at our own galaxy's center, Sagittarius A star. Again, the observations matched predictions. These images provide direct visual evidence that event horizons exist, confirming a fundamental prediction of Einstein's theory in the most extreme gravitational environment. Black holes also raise profound questions about the ultimate fate of information. According to classical general relativity, anything that falls into a black hole crosses the event horizon and hits the singularity, disappearing from the universe. If a book falls into a black hole, the information in that book seems to be destroyed. But quantum mechanics demands that information is never destroyed. Quantum evolution is reversible in principle. This tension between general relativity and quantum mechanics creates the black hole information paradox, one of the deepest puzzles in theoretical physics. Stephen Hawking's discovery that black holes emit thermal radiation, Hawking radiation, due to quantum effects near the horizon, deepened the paradox. Hawking radiation carries energy away from a black hole, causing it to evaporate over immense time scales. For stellar mass black holes, the evaporation time exceeds the current age of the universe by many orders of magnitude. But in principle, a black hole can completely evaporate, leaving only thermal radiation that appears to carry no information about what fell in. This seemingly contradicts quantum mechanics' requirement of information conservation. The resolution of the information paradox remains debated, with proposals ranging from information encoding in subtle correlations, in the Hawking radiation to modifications of space-time structure near the horizon. The paradox highlights that general relativity, despite its successes, cannot be the final theory of gravity. At the quantum scale, and in extreme conditions like black hole interiors, a quantum theory of gravity, not yet fully developed, must take over. Cosmological applications, the expanding universe. General relativity doesn't just describe gravity around individual objects, it provides a framework for understanding the entire universe's structure and evolution. Cosmology, the study of the universe as a whole, became a scientific discipline in the modern sense only after Einstein formulated general relativity, which provided the equations governing cosmic dynamics. The cosmological application of general relativity rests on the cosmological principle, the assumption that the universe, when viewed on sufficiently large scales, is homogeneous and isotropic. Homogeneous means the universe looks the same at every location. There's no special place, no cosmic center or edge. Isotropic means the universe looks the same in every direction. There are no preferred directions, no cosmic axes. These assumptions don't hold locally. Earth is clearly different from intergalactic space, and if you look in different directions from Earth, you see different things. But averaged over scales of hundreds of millions of light years, the universe does appear remarkably uniform. The cosmological principle dramatically constrains the possible forms space-time can take. If the universe is homogeneous and isotropic, its spatial geometry at each moment must be one of three types: flat, positively curved like a three-dimensional sphere, or negatively curved like a three-dimensional saddle. Time remains special. The universe can evolve, expanding, or contracting, but at any given cosmic time, space has a uniform curvature. The metric describing such spacetimes is called the Friedmann-Lemaitre-Robertson-Walker metric, or FLRW metric, named after the physicists who developed it. The FLRW metric contains a function of time called the scale factor, typically denoted A of t, which describes how distances between galaxies grow or shrink as the universe evolves. If the scale factor doubles, all distances between galaxies double. The rate of change of the scale factor determines the universe's expansion rate. Inserting the FLRW metric into Einstein's field equations yields the Friedmann equations, which govern how the scale factor evolves. The first Friedmann's equation relates the square of the expansion rate to the universe's energy density and spatial curvature. Higher energy density drives faster expansion. Positive spatial curvature, like a sphere, slows expansion. Negative curvature, like a saddle, allows faster expansion. The second Friedmann equation, sometimes called the acceleration equation, describes how the expansion rate changes over time. It shows that ordinary matter and radiation cause the expansion to decelerate. Gravity pulls back, slowing the universe's growth. Negative pressure, such as that associated with a cosmological constant or dark energy, causes acceleration. The expansion speeds up over time. In the 1920s, several physicists realized that Einstein's equations naturally predicted a dynamic universe, either expanding or contracting, not the static universe most astronomers assumed existed. Alexander Friedmann in Russia and Georges Lemaitre in Belgium independently derived the equations describing expanding universes. Lemaitre even proposed that the universe began in an extremely hot, dense state, an idea that later developed into the Big Bang theory. Einstein himself had tried to force his equations to allow a static universe by introducing the cosmological constant, effectively adding a repulsive effect to balance gravitational attraction. When Edwin Hubble's observations in 1929 demonstrated that distant galaxies are receding from us with velocities proportional to their distance, Hubble's law, it became clear that the universe is indeed expanding. Einstein reportedly called his introduction of the cosmological constant his greatest blunder, though this story may be apocryphal. The expanding universe solution to Einstein's equations has a remarkable implication. If the universe is expanding now, it must have been smaller and denser in the past. Extrapolating backward, the universe approaches a state of infinite density and temperature at a finite time in the past, the Big Bang. This isn't an explosion happening at some point in space. Rather, it's the origin of space itself, the beginning of space-time. The Big Bang occurred everywhere at once because there was no where before it. The FLRW metric allows three possibilities for spatial geometry, corresponding to three values of spatial curvature: 0, flat; positive, closed, like a three-dimensional sphere; or negative, open, like a three-dimensional saddle. In a flat universe, parallel lines remain parallel forever. The angles in a triangle sum to exactly 180 degrees. Space is infinite in extent. This is the simplest case mathematically, corresponding to exactly critical energy density, the density at which expansion will continue forever, asymptotically approaching zero velocity. In a positively curved, closed universe, parallel lines eventually converge. Triangle angles sum to more than 180 degrees. Space is finite but unbounded. You could travel in a straight line and eventually return to your starting point, like walking around Earth's surface. Such a universe might recollapse in the future if it doesn't contain enough dark energy. In a negatively curved, open universe, parallel lines diverge. Triangle angles sum to less than 180 degrees. Space is infinite, and expansion never stops, even without dark energy. The universe expands forever, with the expansion rate approaching a positive constant. Which type describes our universe? Observations, particularly measurements of the cosmic microwave background radiation's temperature fluctuations, indicate the universe is extremely close to flat, within a fraction of a percent of critical density. This near flatness is not a coincidence, but is explained by cosmic inflation, a brief period of exponentially rapid expansion in the universe's first fraction of a second. Inflation stretched space smooth, driving any initial curvature towards zero. The expansion of the universe means that distant galaxies move away from us, with recession velocities increasing with distance. This doesn't mean galaxies are moving through space away from Earth. Rather, space itself expands, carrying galaxies along with it. The distance between any two galaxies, not bound together by local gravitational forces, increases over time as space stretches. Hubble's law quantifies this expansion. The recession velocity of a galaxy is proportional to its distance, with the proportionality constant called the Hubble constant. Current measurements place the Hubble constant at approximately 70 kilometers per second per megaparsec, meaning a galaxy 1 megaparsec away, about 3.26 million light-years, recedes at 70 kilometers per second. A galaxy 2 megaparsecs away recedes at 140 kilometers per second, and so on. The Hubble constant has units of inverse time, and its inverse gives a rough estimate of the universe's age. With a Hubble constant of 70 kilometers per second per megaparsec, the age comes out to about 14 billion years, close to the more precise age of 13.8 billion years, determined from combining multiple cosmological observations. In recent decades, a startling discovery has reshaped cosmology. Observations of distant supernovae in the late 1990s revealed that the universe's expansion is not slowing down, as ordinary matter's gravity would require, but is accelerating. Galaxies are receding faster now than they were billions of years ago. Something with negative pressure, a repulsive gravitational effect, dominates the universe's energy budget, driving the acceleration. This mysterious component is called dark energy, and it constitutes about 68% of the universe's total energy density. The simplest explanation for dark energy is Einstein's cosmological constant, representing a constant energy density of empty space itself. A cosmological constant produces exactly the negative pressure needed to accelerate expansion. Its value is tiny, about 6 billion electron volts per cubic meter. But because space is so vast, it dominates the universe's dynamics on cosmic scales. The nature of dark energy remains one of the biggest mysteries in physics. Why does it have the observed value? This value is far smaller than theoretical estimates from quantum field theory, which predict a vacuum energy density 120 orders of magnitude larger. This enormous discrepancy, called the cosmological constant problem, has no accepted resolution. Alternative explanations for dark energy, such as dynamical fields that change over time, have been proposed but remain speculative. Dark energy's dominance has consequences for the universe's ultimate fate. If dark energy maintains constant density as the universe expands, as a cosmological constant would, the expansion will continue accelerating forever. In the distant future, galaxies outside our local gravitationally bound group will recede beyond our cosmic horizon, disappearing from view. The universe will become ever more empty and cold, with matter diluted by the relentless expansion. This fate, sometimes called the Big Freeze or heat death, extends trillions of years into the future. General Relativity's cosmological applications connect the smallest scales, the curvature of space-time around individual particles, to the largest scales, the geometry and evolution of the universe itself. The same equations that predict how light bends near the sun also predict how the universe began in a Big Bang and how it will end in an accelerating expansion. This unity across scales exemplifies the elegance and power of Einstein's geometric framework. Experimental confirmations. General relativity makes numerous predictions that differ from Newtonian gravity. Many of these predictions have been confirmed through increasingly precise experiments and observations, establishing the theory as one of the most thoroughly tested frameworks in physics. We've already mentioned three classical tests: the precession of Mercury's perihelion, the deflection of starlight during solar eclipses, and gravitational redshift. Each provided early support for the theory, though measurement precision in Einstein's era left room for alternative explanations. Modern technology has enabled far more stringent tests. Gravitational redshift, the slowing of clocks in gravitational fields, and the corresponding shift of light to longer wavelengths when climbing out of a gravitational potential, was first measured precisely in the Pound-Rebka experiment of 1960. Robert Pound and Glenn Rebka used the Mössbauer effect, which allows extremely precise measurement of photon energies to detect the redshift of gamma rays traveling up a 22.5-meter tower at Harvard University. The measured shift agreed with general relativity's prediction to about 1%. Subsequent experiments have confirmed gravitational redshift with ever-increasing precision, now reaching accuracy better than 1 part in a million. Binary pulsars provided some of the most compelling evidence for general relativity. Pulsars are rapidly rotating neutron stars that emit beams of radio waves. If a pulsar orbits another compact object, the orbital motion causes periodic variations in the pulsar's apparent pulse rate due to Doppler shifts. By timing pulsar pulses with extreme precision, microseconds over years, astronomers can map the orbit with exquisite detail. The first binary pulsar, PSRB 1913 plus 16, was discovered in 1974 by Russell Hulse and Joseph Taylor. It consists of two neutron stars orbiting each other every 7.75 hours. General relativity predicts that such a system should lose energy by emitting gravitational waves, causing the orbit to gradually shrink. The orbital period should decrease at a predictable rate, determined by the masses and orbital parameters. Measurements spanning decades showed the orbital period decreasing by exactly the amount predicted by general relativity, about 76 microseconds per year. The cumulative shift now exceeds a second, and the agreement between theory and observation reaches a fraction of a percent. This orbital decay provided the first indirect evidence for gravitational waves decades before their direct detection. Hulse and Taylor received the 1993 Nobel Prize in Physics for this discovery. The most dramatic recent confirmation came in 2015 with the direct detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, LIGO. Gravitational waves are ripples in space-time curvature that propagate at the speed of light, predicted by general relativity but never directly observed until LIGO's breakthrough. On September 14, 2015, both LIGO detectors, one in Louisiana and one in Washington state, registered a distinctive signal, a brief chirp lasting a fraction of a second, with frequency and amplitude increasing rapidly before cutting off. The signal matched predictions for gravitational waves from two black holes spiraling together and merging. The black holes, with masses of 29 and 36 solar masses, merged 1.3 billion light-years away, releasing 3 solar masses of energy as gravitational waves in the final fraction of a second. The detected signal agreed with general relativity's predictions in exquisite detail. The waveform shape, the frequency evolution, the final frequency at merger all matched computational simulations of black hole collisions in Einstein's theory. This agreement confirmed that black holes exist, that they merge, and that general relativity correctly describes space-time dynamics even in these extreme conditions. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events from black hole mergers, neutron star mergers, and mixed systems. Each detection provides another test of general relativity in strong field, highly dynamic conditions where spacetime is violently warping. So far, all observations agree with the theory's predictions. No deviations have been found. Gravitational wave astronomy has opened an entirely new window on the universe. Events that emit little or no electromagnetic radiation, black hole mergers for instance, are invisible to traditional telescopes but shine brightly in gravitational waves. The detection of gravitational waves from a neutron star merger in 2017, followed milliseconds later by gamma rays and subsequently by optical, infrared, and radio emission, demonstrated multi-messenger astronomy combining gravitational waves with light. This event confirmed that neutron star mergers are the source of heavy elements like gold and platinum formed in the extreme conditions of the merger and ejected into space. Precision tests of general relativity continue in the solar system. The Cassini spacecraft, orbiting Saturn from 2004 to 2017, enabled tests of general relativity by tracking radio signals passing near the Sun. As Earth and Cassini moved to positions where the Sun lay nearly between them, radio signals traversed regions of strong space-time curvature. The signal delay, due to this curvature, the Shapiro time delay, predicted by general relativity, was measured with precision better than 0.001%, agreeing perfectly with theory. Gravity Probe B, launched in 2004, tested two predictions of general relativity related to Earth's rotation: frame dragging and geodetic precession. The satellite carried 4 gyroscopes, the most perfect spheres ever manufactured, and measured how their spin axes changed over a year in orbit. General relativity predicts two effects: geodetic precession, caused by the curvature of space-time around Earth's mass, and frame dragging, caused by Earth's rotation dragging space-time around with it. Both effects were detected, matching predictions to within the measurement uncertainties after careful analysis of systematic errors. The Event Horizon Telescope's black hole images, mentioned earlier, represent yet another confirmation. The size of the black hole shadow depends on the black hole's mass and the theory of gravity. General relativity makes specific predictions for shadow size and shape. The observed shadows of M87's black hole and Sagittarius A star agree with general relativity's predictions, ruling out some alternative theories of gravity that would produce different shadow shapes. Tests continue with ever-improving precision. Atomic clocks have become so accurate that they can detect gravitational redshift over height differences of centimeters. Pulsar timing arrays, monitoring many pulsars across the sky, are searching for gravitational wave background from supermassive black hole mergers throughout the universe. Future space-based gravitational wave detectors will detect waves from sources LIGO cannot observe, further testing the theory in different regimes. No confirmed deviation from general relativity has been found in any experiment or observation, despite tests spanning scales from millimeters to billions of light years and field strengths from Earth's weak gravity to black hole event horizons. The theory has passed every test with remarkable success, confirming Einstein's vision of gravity as space-time geometry. The deeper meaning. Einstein's geometric theory of gravity represents more than just a refinement of Newton's laws. It embodies a profound philosophical shift in how we understand the relationship between matter, space, and time. The theory dissolves boundaries that once seemed fundamental between space and time, between geometry and physics, between reference frames in motion and reference frames at rest. In pre-relativistic physics, space and time formed an absolute background, an unchanging stage on which physical events unfolded. Matter and energy moved through space, evolved in time, and interacted through forces propagating across space. But the stage itself remained passive, unaffected by the drama it hosted. General relativity overturns this picture completely. Space-time is not a passive arena, but an active participant in physics. Matter and energy shape space-time's geometry, and that geometry in turn guides matter's motion. The stage and the actors engage in a dynamic interplay, each influencing the other continuously. This unification of geometry and physics has deep aesthetic appeal. The geometric structures studied by mathematicians, manifolds, curvature, geodesics, turn out to describe physical reality. Abstract mathematical concepts become concrete physical predictions. The Riemann curvature tensor, developed in the mid-1800s as pure mathematics with no thought of physical application, becomes the key to understanding gravitational tidal forces. Geodesics, the subject of differential geometry, become the paths followed by freely falling objects and light rays. Einstein himself was struck by the elegance of the theory's mathematical structure. He later wrote that the right-hand side of his field equations, representing matter and energy, seemed crude and ugly compared to the geometric beauty of the left-hand side, representing space-time curvature. This perception hints at something deep. Perhaps matter itself has a geometric origin. Perhaps what we call particles and fields are manifestations of space-time geometry in ways we don't yet fully understand. The equivalence principle, the inability to distinguish gravity from acceleration locally, implies something radical about the nature of gravitational force. In Newtonian mechanics, gravity is one force among others: gravitational force, electromagnetic force, tension, friction. But in general relativity, gravity isn't a force at all. It's the manifestation of space-time geometry. An astronaut in orbit feels weightless, not because gravity has been cancelled, but because she is following a geodesic, the natural path through space-time. The force she would feel standing on Earth's surface is the non-gravitational force of the ground pushing her off the geodesic she would naturally follow. This reconceptualization suggests a program. Perhaps other forces can be geometrized. If gravity is geometry, might electromagnetism, the strong force, and the weak force also be geometric in some sense? Einstein spent the last decades of his life pursuing unified field theories, attempting to realize this vision. His attempts failed, but the impulse behind them, the desire to understand all forces as manifestations of geometry, continues to inspire theoretical physicists. Modern theories, like string theory and loop quantum gravity, seek to fulfill this vision, though in ways Einstein never imagined. General relativity also forces us to rethink the concept of time. In Newtonian physics, time is universal. Clocks everywhere tick at the same rate, and simultaneity is absolute. Two events either occur at the same time or they don't, regardless of observer motion. Special relativity fractured this picture, making simultaneity relative to reference frame, but preserving the idea that in some sense space-time can be foliated into slices of constant time. General relativity goes further. In curved space-time, there is generally no natural way to define a global time coordinate. The splitting of space-time into space and time becomes observer-dependent in a deep way. Near a black hole's event horizon, the time coordinate and radial coordinate in some sense swap roles. Inside the horizon, the singularity lies not in some direction in space, but in the future. You can no more avoid hitting the singularity than you can avoid reaching tomorrow. This intermingling of space and time reaches its extreme in cosmology. The Big Bang is not an event in time, but the beginning of time. Asking what happened before the Big Bang is like asking what lies north of the North Pole. The question itself is misformed because before presupposes time, and time begins at the Big Bang. Spacetime, as a four-dimensional entity, has a boundary, an edge at the Big Bang. But this boundary is space-like rather than time-like. It's more like a spatial boundary than a temporal one. Despite its successes, general relativity cannot be the final word. The theory is classical, treating space-time as a smooth continuum. But we know that at sufficiently small scales, quantum effects become important. At distances around the Planck length, about 10 to the negative 35 meters, quantum fluctuations of space-time geometry itself should become significant. At such scales, the smooth manifold picture breaks down. Space-time might become discrete or foam-like, or something even more exotic. Moreover, general relativity predicts its own limitations. Singularities, places where curvature becomes infinite, appear unavoidably in black holes and at the Big Bang. At singularities, the classical theory breaks down. Physical quantities become infinite, and predictions become impossible. Singularities are signals that the theory is incomplete, that new physics must take over in these extreme regimes. The quest for quantum gravity, a theory that reconciles general relativity with quantum mechanics, has occupied theoretical physicists for decades. Numerous approaches have been explored: string theory, loop quantum gravity, causal set theory, asymptotic safety, emergent gravity. Each offers insights, but a complete, experimentally verified quantum theory of gravity remains elusive. The difficulty is partly observational. Quantum gravitational effects become important only at energy scales far beyond any particle accelerator's reach, or in extreme environments like black hole singularities or the Big Bang's first instance, places we cannot directly probe. Testing quantum gravity theories requires extraordinary ingenuity, searching for subtle effects that might appear in gravitational waves, cosmological observations, or precision measurements of gravity at short distances. Yet the pursuit continues, driven by the same impulse that drove Einstein: the desire to understand nature's deep structure, to unify disparate phenomena under common principles, to see the universe as a coherent whole. General relativity, with its geometric elegance and empirical success, stands as both an achievement in its own right and a stepping stone toward deeper understanding. The theory has transformed how we view reality. It has given us black holes and gravitational waves, the expanding universe and the Big Bang, gravitational lensing and time dilation. It has made precise predictions confirmed across scales from laboratory to cosmos. It has unified space and time, matter and geometry in a framework of breathtaking mathematical beauty. Einstein once remarked that the most incomprehensible thing about the universe is that it is comprehensible, that we can understand gravity, the force that holds planets in orbits, binds galaxies together, and shapes the cosmos, as nothing more than the geometry of space-time is perhaps the deepest example of this comprehensibility. The universe's structure can be encoded in a single tensor equation, relating geometry to matter. This elegant simplicity underlies all cosmic complexity, from the gentle curve of Earth's orbit to the violent collision of black holes. The geometry of space-time reveals that the universe is not a collection of objects moving through empty space and evolving in time. Rather, it is a four-dimensional structure, curved and warped by energy and momentum, dynamically evolving according to geometric laws. We are not in the universe. We are part of space-time itself, localized patterns in the cosmic geometry, following geodesics through a landscape we ourselves help to shape. This vision, matter and geometry united in a dynamic dance, each determining the other, stands as one of humanity's greatest intellectual achievements. It transforms gravity from a mysterious force acting at a distance into the natural motion of objects following space-time's contours. It explains phenomena Newton could never have imagined while encompassing his theory as a special case. It provides the framework for understanding the universe's larger-scale structure and evolution. And yet, for all its successes, general relativity points beyond itself. The singularities it predicts signal its incompleteness. The quantization of matter and fields demands a quantum description of spacetime as well. The unification of gravity with other forces remains an open challenge. The nature of dark matter and dark energy, components that dominate the universe's mass energy but interact only gravitationally, remains mysterious. Each answer raises new questions. Each solved puzzle reveals deeper layers waiting to be explored. This is the nature of physics. Each successful theory becomes the foundation for the next. Each mystery resolved opens new horizons. General relativity itself emerged from pondering the mysteries left by Newtonian gravity and special relativity. Whatever theory eventually supersedes, it will build on its insights, preserving its successes while explaining the phenomena it cannot. The geometry of space-time will remain a fundamental concept, even as we discover new structures underlying or emerging from it. For now, general relativity stands as our best understanding of gravity and space-time. Its predictions match every observation. Its mathematical structure exhibits profound beauty, and its conceptual framework has reshaped our understanding of physical reality. When we observe starlight bending around the sun, detect gravitational waves from colliding black holes, or measure time dilation between mountaintop and valley, we are witnessing space-time geometry in action, Einstein's elegant curvature made manifest. The theory invites us to see the universe not as objects in space, but as space-time itself, a four-dimensional manifold whose curvature encodes gravitational phenomena, whose geodesics guide matter's motion, whose dynamics govern cosmic evolution. This perspective, hard-won through decades of mathematical development and empirical testing, represents one of the deepest insights human thought has achieved into nature's workings. Understanding general relativity means grasping that the falling apple and the orbiting planet, the bending light and the slowing clock, the colliding black holes and the expanding universe, all these phenomena arise from a single underlying reality, the geometry of space-time, curved by matter and energy, determining the paths all things follow through the cosmos. This is Einstein's legacy, a universe understood not through forces acting between objects, but through the shape of space-time itself. It is gravity revealed as geometry, motion revealed as following space-time's curves, the cosmos revealed as a dynamic four-dimensional structure obeying elegant mathematical laws. The geometry of space-time, Einstein's elegant curvature, describes not just how gravity works, but how the universe itself is woven together, space and time and matter unified in a geometric vision of uncommon beauty and explanatory power. As we close, consider that every moment of your existence traces a world line through space-time. You are not moving through space as time passes. You are moving through space-time, following a time-like curve from past to future. The ground beneath your feet constantly accelerates you away from the geodesic you would naturally follow. The ticking of your clock measures proper time along your world line, influenced by the gravitational potential in which you live. You are embedded in space-time's geometry, feeling its curvature as weight, experiencing its dynamics as change. The next time you feel gravity's pull, remember, you're not feeling a force reaching across space to attract you downward. You're feeling space-time's curvature, the geometric structure of reality itself, as the ground accelerates you away from the path you would naturally follow through the four-dimensional landscape that is our universe. Gravity is geometry. Mass curves space-time, and we, along with everything else, follow the straightest possible paths through that curvature, geodesics in Einstein's elegant geometry. If you've found this journey through curved space-time illuminating, please consider liking this video and subscribing to Whispering Science. Your support allows us to continue exploring the deep structures underlying reality, one concept at a time, in the quiet hours when the mind is ready to wander through physics and mathematics, through space and time, through the elegant geometry that shapes everything that is. Sleep well, and may your dreams trace geodesics through peaceful regions of space-time.